All right, welcome back everyone to the second morning session today. We're going to go ahead and get started, and people will just kind of trickle in throughout. So, first talk of this session is from Xirui Wang of MIT. She's from Professor Pablo Horio Herrero's group, and she's going to tell us about sliding ferroelectricity, which just sounds awesome. I'm really interested to find out what that is. So, please.
Yeah, thank you, Austin. Thank you, everyone. So I'm Xirui Wang from MIT, and I'm very honored to be here to participate in this Precision in 2D Materials seminar held by CNS. So you will see in the following that actually more than half of the work that I present is actually conducted here at CNS. So I myself is a very heavy CNS user. So the topic I'm going to present today is Van der Waals engineering of sliding ferroelectricity. So this is my outline. First, I will mention about the designing principle for engineering the sliding ferroelectricity in 2D materials by stacking two monolayers of the Van der Waals material in a particular stacking order. That involves the boron nitride and transition metal dichalcogenase. And afterwards, I will mention that when these two monolayers are stacked in a parallel stacking manner, they exhibit this ultra-fast and high endurance switching. And on the other hand, when there is a small twist angle between the monolayers, they can be used as a Moiré polar substrate to engineer the band structure of the target material on top of it. So before we go into sliding ferroelectricity, let's recap a little bit on ferroelectricity. Ferroelectrics is a kind of material that has a spontaneous polarization. So take this conventional ferroelectric barium titanium, for example. Before the phase transition, this titanium ion is in the center of this oxygen octahedral. And when it goes through the phase transition, this titanium ion will displace from the center, and that gives rise to an downward electric field. So this spontaneous polarization makes ferroelectric material very promising candidate for non-volatile memories because the polarization stays constant and non-zero without the external electric field or voltage. And the magnitude and direction can be used as the memory unit. So thinning down this ferroelectric material is very important for denser storage and lower consumption. However, most of these conventional ferroelectric material are in the 3D bulk form. So this strong bonding between the atoms make it very hard to thin down below 100 nanometer while still maintaining its ferroelectricity. So here, I want to introduce this material platform called Van der Waals materials. So this kind of material is kind of having a layered structure, and between the layers, the interlayer bonding is the Van der Waals force. So it's pretty weak, and you can easily exfoliate them down to monolayers. And then what's more intriguing is that by stacking the same or the different monolayers on top of the other, you can design the functional properties that is absent in a single crystal, just like these Lego building blocks. So how are we going to engineer this ferroelectricity using Van der Waals materials? The material that we choose is boron nitride. This is very commonly used to the insulator. So the structure is like this. The monolayer boron nitride takes this honeycomb lattice similar to the graphene, while instead of the carbon, it has these boron and nitrogen atoms alternatively occupying the site. This naturally grown boron nitride in the bulk form is taking this hexagonal stacking order. We call it HBN. And in particular, if we just consider two adjacent layers, they take this anti-parallel stacking manner. So basically, the top and bottom layer is 180 degrees rotated. So here you would see that the nitrogen sits on top of the boron, while this boron sits on top of this nitrogen. So in total, this inversion symmetry guarantees that there is no net polarization in this hexagonal stacked boron nitride. But if we consider it another way, we take a monolayer and we use some method to cut it into half, and then we stack them on top of each other. Then we end up with this thermodynamically stable phase called AB stacking, which here you can see that this boron sits on top of this nitrogen, while this nitrogen doesn't have any boron beneath it. So in total, this inversion symmetry is broken because of this asymmetry between the boron and nitrogen atoms. So this can potentially give you the polarization. Exactly how this works is that if you consider this boron and nitrogen, basically the boron has an empty 2pz orbital and the nitrogen has a filled 2pz orbital. When these two hybridize, this gives rise to this distortion of the electron cloud, and the electrons moves towards the boron atom, and you have a downward polarization. And if we consider more completely about the phase space, actually besides this AP-stacked boron nitride, we also have the energetically degenerate BA-stacked boron nitride, where you have this nitrogen sitting on top of the boron in this structure. And these two can translate into each other through this interlayer sliding motion by 1/3 of the unit cell, while they have the opposite out-of-plane polarization. So now in theory, we have demonstrated that we can have this out-of-plane dipole from this interfacial interaction between the two layers. So now we want to experimentally verify that. To do that, we take two monolayers and twist a small angle between the two. So now we have this long wavelength Moiré pattern as shown here. And at different Moiré sites, we have these different stacking orders, A, B, BA, and AA stacking. So this AA stacking, because it has the two layers exactly aligned, this has a much higher energy cost, and the AA site will shrink, while AB and BA will expand to these triangular networks after the lattice relaxation. So this is exactly what we discovered in the experiment using the piezoelectric force microscopy. We see that there is the alternating triangles pointing upward and downward, and the adjacent two have the opposite contrast, which means that they have opposite out-of-plane polarization, pointing to the AB and BA. So besides the spontaneous polarization, another important character of the ferroelectrics is the switchability under the external electric field. So to study that, we need to control the electric field that the bilayer BN feels. So we have this heterostructure where this graphene is used as an electronic sensor to sense the polarization in the parallel stack BN, and the top and bottom gate is to use to control the doping and the electric field. So I should mention that these two thicker boron nitride on the top and bottom are just gate dielectrics, so they are not ferroelectric materials. So this effective field effect transistor structure works like this. So depending on the polarization on this bilayer boron nitride, whether it's up or down, it can either induce electrons or holes into the graphene and lead to the resistance shift in graphene. First, we scan the top gate. And then we see a single resistance peak in the graphene. So this corresponds to the Dirac point in graphene, which is a typical behavior that we observe. And very interestingly, when we scan the bottom gate, we see that when we scan in the forward direction, we see a single resistance peak. And when we scan in the backward direction, we also see a resistance peak, but these two have a clear shift. And in addition, at around 1.9 volt, there is a clear resistance jump in the graphene measurement. So these two behaviors actually correspond to the ferroelectric switching in this parallel stacked BN. And this red curve and blue curve, for example, correspond to the upward and downward polarization in the boron nitride, respectively. Oh, by the way, so the reason that we only see it in the back gate is because the top gate is mostly screened by this graphene on top, so that it doesn't really apply any electric field to the bottom bilayer BN. So using this characteristic, we can actually perform this dual gate map where we have this top gate voltage as the fast scanning axis, so that it is only used to probe the polarization. And this bottom gate is the slow scan axis to control the electric field. So we see some interesting behavior at two contact pairs that we measure. So in one of the contact pair, we see a clear change from the AB to BA domains here. Well, on the other contact pair that we measure, we see a coexistence of the two peaks. So this actually tells us that in the contact pair 2 region, we have coexistence of the AB and BA domain. And this switching dynamics can be very sensitive to these local stacking configurations. So now we want to quantify the polarization in the parallel stack BN based on the charge carrier density induced in the graphene. So here we build a simple electrostatic model, and then we consider this monolayer graphene, parallel stack BN, bottom BN dielectric, and the metal gate. The relation we get is that the charge carrier density induced in graphene is inversely proportional to the total bottom BN thickness, and their product is proportional to the polarization in the BN. So our experimental data plotted based on the carrier density induced in graphene as a function of the bottom BN thickness agrees with the theoretical curve that showing inserting the thicker boron nitride will make the modulation in graphene smaller. And at the same time, the magnitude of the polarization also agrees with the theoretical calculation. So the previous measurements were performed at 4 Kelvin, but even if we warm up to the room temperature, we still see this robust ferroelectric switching, and the retention time is over a month without applying any external electric field. So this is because of this particular stacking order, and it has a very high energy cost if you want to melt down this ferroelectric order, because then you have to completely change the twist angle. And this can be used as this proof of principle demonstration for the ferroelectric FET. So if we examine a little bit about the key ingredients that we need for this sliding ferroelectricity, we first need a honeycomb lattice, and then we need this bipartite composition so that, for example, we have this asymmetry between the boron and nitrogen atoms. So using this designing principle, we can extend to other materials that also obey these two rules. So a material that first come to our mind is the transition metal dichalcogenides. So transition metal dichalcogenides, if you take a look from the top view, it has the same lattice structure. Basically, it's a honeycomb structure, and then you also have this M atom and X atom. So if you look from the side, it's a little bit different because for the boron nitride, both the boron and nitrogen are in the same plane. But here, the X atom is on the top and bottom of the M atom. But the initial gradient is the same. And if you consider when they are stacked in the parallel stacking manner, this will break the inversion symmetry and lead to the upward and downward polarization. And these two can also change into each other through this interlayer sliding motion by 1/3 of the unit cell. So using PFM, we can also successfully examine these upward and downward polarized domains in these triangular networks. So using the same strategy, we can fabricate this graphene sensing structure. And in 4 TMD materials, WSC2, MOSC2, WS2, and MOS2, we all observe this clear ferroelectric switching behavior. And this tells us that all of these 4 TMDs are ferroelectric. So now we want to study a little bit more about what is exactly happening during this ferroelectric switching. So to perform that, we fabricate this device with a parallel stacked MOSC2 and control it with a graphite bottom gate. So here is a video, and basically for this imaging, we are using this lateral piezoelectric force microscopy. So instead of these domains, it's more sensitive to this domain wall motion. And amplitude and phase image are telling you basically the similar information, and for easier guidance, we draw this schematic, and this different red and blue means the up and down polarizations. And we can So we can take a snapshot of this ferroelectric switching. So from this downward polarization to this, for this negative to the positive voltage, we see that this up polarization gradually dominate. And this domain switching process happens through this domain wall motion during the process, rather than a domain nucleation, for example, from the center of the device. So it means that in our device, at least, the energy cost for this domain wall motion is much smaller. And we also noticed that these bubbles and the cracks are really as a domain pinning site during the ferroelectric switching. All these four new discovered TMT materials are also robust up to the room temperature for the ferroelectric switching. So up to the time when we discovered these 5 new materials, this nearly doubles the existence to the ferroelectric family. So we can compare the built-in interlayer potential in these 5 sliding ferroelectric materials. So the interlayer potential is basically the potential between the parallel stacked TMD or the parallel stacked BN. And our experiment gives a rate down that the delta VP is around 110 MeV for the boron nitride, and the value is about half for the other 4 TMDs. And they also agree with the DFT calculation. And we can also compare these sliding ferroelectric material with other types of van der Waals ferroelectric materials. So for example, this copper indium phosphor sulfide or this indium selenide, their designing principle is to start from a bulk polar material and then using this top-down principle to exfoliate them down to thin layers. While in our case, we are actually building this non-ferroelectric monolayer by stacking them with a particular stacking order and turn a non-ferroelectric into a ferroelectric material. So this designing principle can be extended to many material candidates, so it actually opens a large designing space. The polarization in our case comes from this charge redistribution, while in the other cases, it's mainly from the ion displacement. And I think the main difference of the switching mechanism is that in our case, the outer plane electric field is through this interlayer sliding motion, while in the other case, it's mainly through this intralayer motion. So because we know that this van der Waals force between the layers is pretty weak, and sometimes it has this super lubricant motion between the 2 layers. So maybe this sliding ferroelectric can be a potential candidate for high-performance ferroelectric materials. Yeah, so to study that, we apply electric pulses to study this ferroelectric switching dynamics. So first, we studied the switching voltage as a function of the switching time. So what we do is that we first initialize the polarization to one state, and then we apply a pulse with a negative polarity. And by varying this pulse duration and this pulse magnitude, we examine at which voltage we have this polarization switching. So we can see that as the pulse duration gets longer, the voltage we need to switch is getting smaller. This agrees with the typical ferroelectric switching behavior. And more importantly, even down to 1 nanosecond, we still successfully see the switching. So this is kind of the ultra-fast switching, which is comparable to the state-of-the-art performance of this hafnium oxide ferroelectric FET. And on the other hand, we also perform this switching experiment up to 10 to the 11th cycle, and we see that up to this value, there is still a very robust ferroelectric switching behavior, also comparable to the state-of-the-art performance. We think that there is no degradation up to this number of cycles because of this van der Waals nature of the interface, because usually these defects trapped at this interface will gradually degrade your ferroelectric materials. So far, we have been mainly studying this real space switching dynamics in this parallel stacked boron nitride, and we examine the switching behavior using graphene mainly as a sensor material. But on the other hand, actually, we already mentioned that using the twisted boron nitride, we can make this Moiré structure where you have these alternating up and down polarizations forming this superlattice potential. So can we use it as the Moiré substrate to engineer the band structure of the material on top of it, basically from the real space turn to the momentum space modulation? So to study that, we fabricate the device using the twisted boron nitride as a substrate and use it bilayer graphene as a target material. So from our electrostatic simulation, we expect around 30 MeV of the superlattice modulation in the graphene, and this can lead to this the formation of the mini brilliant zone and this band folding in the bilayer graphene, which will open these small local gaps at the fulfillings of the conduction band and valence band of the Moiré mini brilliant zone. This is our experimental result. So the longitudinal resistance shows clear satellite resistance peaks apart from the charge neutral point. And on the same time, we see that in the RYX measurement, there is a clear sign reversal at the fulfilling and also before the fulfilling. So we think that they probably correspond to the Van Hoff singularities. So we can fabricate more devices with a different twist angle, and then we can study devices with a different Moiré wavelengths. So for all of these materials, we see these satellite resistance peaks. And by comparing with our PFM image before the fabrication, we actually can really now assign these satellite resistance peaks to be the fulfilling of the Moiré bands. By applying the magnetic field, we can observe this magnetotransport. For example, these Landau fans emanating from this satellite resistance point, and we can also see these clear Brown-Zach oscillations as the enhanced conductance of these horizontal lines. So that corresponds to the commensurability between this magnetic unit cell and the Moiré unit cell. We also observe this diminishing of the sign reversal as you increase the magnetic field, and that's due to the competition between the cyclotron energy and the Moiré band gap. So previously, we mentioned that with a thicker BN, we can tune the modulation in the graphene. So that was in the parallel stack case, but it also holds true for the twisted BN case. If we insert a thicker BN, we can expect the modulation to be decreased from around 30 to around 10 MeV. To verify that, we fabricate device with both without and with the bottom BN. And in this device with the bottom HBN, we still see these clear satellite resistance peaks, but the peak height is much smaller. So that indicates that we have a small Moiré modulation. So we have devices with different Moiré wavelengths, and the comparison is clear for all these devices. And we can also examine their magnetotransport structure. And for example, in the case with the bottom BN, we still see these Brown-Zach oscillations, but the strength is much weaker. And on the sigma xy, we also see the sign reversal, but the critical magnetic field is also much smaller. So they all indicate that by inserting the thicker BN, we successfully tune down the Moiré potential. So lastly, I want to mention that we also fabricate device by twisting around 60 degrees for the twisted bilayer BN. So naively thinking, this 60-degree twisted BN is very close to the 180-degree one because of the threefold symmetry. And therefore, if you just consider this stacking order, actually for all of them, you have this inversion center between these two layers, so that there shouldn't be any electrostatic effect from these polar domains. However, in the experimental result, we actually still clearly see these satellite resistance peaks on the two sides of the central Dirac peak. And in the same time, it's maybe more clear in this dual gate map for these two satellite resistance peaks and in this magnetotransport measurement. So they still clearly exist, and where does it come from? So there are a few theoretical perspectives that we think of. So one is that basically during this lattice relaxation, you can have this in-plane strain. And this in-plane strain can lead to some charge redistribution that give you the out-of-plane polarization. So that's one possibility. And the other possibility is that this out-of-plane corrugation comes from this varying of the interlayer distance within the Moiré unit cell. So this corrugation can lead to the difference in the tunneling strength between the two monolayers of graphene, and this may also give you some Moiré modulation. So exactly what mechanism is dominating will require further experimental and theoretical studies. So, so far people have been using a few different ways to impose the Moiré potential to the to the 2D materials. So for example, when people align the graphene to the boron nitride, it has a very small Moiré disorder because of this lattice mismatch, but the Moiré periodicity is limited, and you have some limited material choice. So people also use this pattern dielectric gating, where they punch the holes by the lithography. So in that case, it's very versatile in the terms of materials and gate voltage, but the problem is lithography capacity, which is limited to around 16 nanometers. So the advantage of the Moiré polar substrate is that it can be applied to any materials and with any Moiré wavelengths. So I should still mention that the twist angle disorder is kind of a potential limitation, and we still are trying to a different fabrication method to improve that. So to summarize, I have demonstrated the Van Waals engineering of sliding ferroelectricity, and so the parallel stacked BN has the ultra-fast and high endurance switching, while when we twist a small angle, we can use it as a Moiré polar substrate. So in the future, I think there are many exciting directions to explore, and I can mention a few of it. For example, now we have demonstrated nanosecond switching, but it's actually not limited by the device itself, but limited by the instrument. So if we apply ultra-fast pulses like picometers by the optics, we can probably even image the faster switching speed. And application-wise, it will be interesting to study the size dependence and the layer dependence of the switching. And using this Moiré twisted substrate, we can also apply to other target material with a flatter band by the graphene and potentially see the correlated interesting physics. And we can also study how to use the pressure to tune the potential strength and increase the Moiré modulation. So with that, I would like to thank my collaborators at MIT, my advisor Pablo, and my collaborator Kenji, etc. And I got lots of theoretical support from Yang Zhang's group, Liang Fu's group, and Kaxira's group. The crystals are from Colombia for the TMD ones, and for the BN, it's from NIMS in Japan. And lastly, I would like to acknowledge these funding agencies, and especially I want to mention that all of these PFM imaging and actually the post-processing of these field effect transistor structures is all done here at CNS, and the PFM imaging is especially done with the help of Jason, who is also in the conference today. Yeah, thank you.
All right, thank you for some extremely cool results. We have time for one question or thereabouts.
Hi. So I had a question about twisting monolayer boron nitride. I know this is a very hard task. What method did you use to twist monolayer of boron nitride?
Yeah, it's actually not as hard as people think. It's the same idea as twisting the graphene, whatever. Yeah, you basically use a thicker boron nitride, and then you engage into a monolayer BN. You pick it up. By just picking it up, you can tear it, and then you engage to pick another one.
So you tear the layer during the pickup, you stop halfway, tear it up, and rotate the bottom.
Exactly, yeah.
How repeatable is your procedure, and how much of angle control do you have for that?
I think its difficulty is basically similar to graphene process.
Okay.
Like, I think if we target a specific angle, success rate is not that high, but it's like 50%. So also acceptable.
Thank you.
Yeah.
Okay, in the interest of time, I think we're going to move on to our next speaker, but let's thank our speaker again.
Thank you.